Okay, we're at the start time. Let's see. We have probably a bunch of people who are going to be coming in. As I'm Michael J. I'm the chair of the IEEE Icicle, and here with me is also my vice chair, and that's Jody Liss, who will wave to you. Yes, there we go. And a number of my other colleagues. We're a really collegial group, and presenting in today's session on behalf of IEEE Icicle are, as I've already mentioned, Jody Liss. Zarka Ali, Wave Zarka, who is in Pakistan right now, and John Costa. There we go. And in the background, whose name you can just see possibly is Renee Johnson, and she is doing all that back end work. Oh, also Ann Fency. Where's Ann? There she is, waving away. So, um, uh, really great to see all of you here. I'm sure we're going to get more people coming in. But as I said, this is really brought to you by all the members of Icicle, and we definitely look forward to having you engage with Icicle as well. Today's agenda. Um, Thanks, Renee. We'll do a quick welcome, which I'm doing right now, and I'm doing some introductions. Also, we'll do a quick overview of what is learning engineering, and then we'll put the learning engineering into practice. And this is where our colleagues from Carnegie Learning are going to be discussing that. And those are Steve Ritter and Ray Bastoni and Husni, whose last name I am not going to try to destroy. So good to see you, all three of you. And then we'll go into a live Q&A. That's where, again, please do put your questions into the chat or into the Q&A section. And then John will be talking a little bit about Icicle SIGs and MIGs, the market interest groups. We'll talk a little bit about learning engineering resources, and then an invitation for all of you, each of you, to get engaged with IEEE Icicle and learning engineering. Next slide. So many of you, I know I got questions from people already in advance, and that is, what is learning engineering? And most importantly, so there's a poll that just went up about your experience with learning engineering. So if you could respond to that, that would be great. And learning engineering, really the most important part of learning engineering is that it's a process and a practice. And so it really applies learning sciences, human-centered design, and data-informed decision making as part of this iterative process to really engage with the content, the design, the effort in an iterative and data-informed fashion. So as you see below here, learning engineering is a repeatable process intended to iteratively test, adjust, and improve conditions of learning. So in terms of familiarity, we have a real mix of people here. People who are it couldn't get much closer to third, and a third. So we'll try to address everybody's interests as we get going. All right. Next slide. One of the key questions that we always get is, so isn't this just learning science? I mean, is this just a new name for something we've been doing all along? And the bottom line is, no, not really. And the reason is that when we think about science, the goal of science is really to discover some sort of truth, and the investigation is around discovering sort of those core understandings. It's not necessarily about the application. And that's when we end up moving to the engineering side. So you think about STEM, which includes both science and engineering. They're not the same thing. Engineering really has a goal of addressing a problem, looking for scalable solutions to those problems, and then using the science and other aspects as part of that endeavor. So important that there really is a difference between the two in terms of how you should be thinking about that. Let's go to the next slide. So, what's with this term learning engineering? People ask that often. So, is it learning engineering or learning engineering? emphasis. So it's a little bit like these terms: jumbo shrimp, awfully good; baggy tights, civil war; even odds, intense apathy, freezer burn, seriously funny. They're these terms that we sort of hear used side by side. And in terms of unpacking that, you need to think about this as being learning, um, as the adjective, engineering as a verb, not learning engineering. And that's where I think people often get tripped up, and we often have to apologize and explain to people. But it really is the emphasis on using engineering processes and applying that to learning and creating learning experiences of different sorts. Next slide.
So learning engineering is not new. It was introduced in 1967 by Nobel laureate Herb Simon in the paper Job of a College President. And he wrote, "The most important step is to find a place on the campus for a team of individuals who are professionals in the design of learning environments, learning engineers, if you will." So he coined the term, and then in the Simon Initiative was launched at CMU in 2014 to harness work that the university had been doing around learning engineering. And then in 2017, the IEEE launched what is known today as the International Consortium on Innovation and Collaboration for Learning Engineering, and ICICLE was formed. The definition that you just heard stemmed from the ICICLE conference in 2019. And in 2023, the Learning Engineering Toolkit was published. And then just this last year, the learning engineering expanded across academia and into the military. So you'll hear also in corporate settings how Carnegie Learning is using it in this session today. And the Air Force launched the Enterprise Learning Engineering Center of Excellence this year. And then if we can go to the next slide, we have our learning engineering toolkit. There are many, many, many resources in here for people who are new to the field or have some experience in different areas. And there is a bunch of explanations, but then there are lots of actual tools for how do I do this kind of work. So on your screen, you have a poll question, and we want to know how familiar you are with the book. So is this the first time you're hearing about it? Or have you heard about it already? Or are you actually using it? Or can you quote it from memory? I know some of us can, because we pull out this book all the time because there's so many great resources in here. And then you can go to the next slide while that poll question is up. So just a little bit more about ICICLE. So as we noted, ICICLE, oh, good, we've got some new people who have never heard of this book before. So you're going to go out and buy this. But before you do, you can get open access to the first 2 chapters to test it out and see what it's like, and just see how good of a book this is. And it is really nice to see that 29% of people use it as a resource. So that's really excellent that people are using this book. And it's not just me saying how great it is. And I'm not an author. So we do actually have a lot of the authors on the call here today. So feel free to ask them questions about the book. So as I noted in the timeline, ICICLE started in 2017. And what's awesome about learning engineering is that it really is interdisciplinary. So it is a profession, a practice, and a process all in one. And we use it across sectors and disciplines like academia, government, military, corporate, K-12, higher education. And some of the roles and positions range across these sectors, and you can see some of those listed here. So we have been having monthly meetings since 2018, and we have special interest groups that also meet monthly that look at learning engineering from many different perspectives, like how to design using learning engineering, what tools are used in learning engineering, what the skills to do learning engineering are, how to apply learning engineering in K-12 or higher ed or corporate and military. And we'll show you how to join those SIG and MIG groups at the end of this session.
Great. So we've been talking a lot about what is learning engineering. Now it's time to talk about the how. The process that you see here is what's described in the Learning Engineering Toolkit. It's most likely similar to some of the other models you're familiar with when designing a project. The steps are pretty universal, but what's a little bit special about this process? So the first component that you see in the middle is about the challenge, because everything we do around learning engineering revolves around what the challenge is. What's your critical need? What's the opportunity? What's the problem to be solved? And then you'll see on that outer circle encompassing the process is the context, the learners, and the team. So first talking about the context. The issue or the challenge is not isolated. Learning engineering brings in all the different variables in the context. You need to consider the external environment, such as policies or budget. You may consider the leadership. What's the learning environment? What are the resources? It's a real world solution that we're trying to do. The learner, we talked about human-centered. What are the characteristics of your learners? What's their background, their culture, their skills, their needs? And then the team, all projects take a village, and you'll need multiple roles and disciplines to build that solution and implement it to your challenge. So who's going to be on your team? And we want to know, well, what is your most pressing learning challenge? We're really curious to understand more about some of the things that you're facing, and so we can learn from each other. Then the next component is about creation. You're building the solution, and the creation takes several aspects. We talked again about the human-centered, so you consider the learning, and you're also bringing in multiple stakeholders, including the learner, into the design of the solution. You're looking at those learning sciences. What are those methodologies and approaches that you can apply to the solution? Learning engineering helps to build that evidence to practice. Data, that's going to be something you're going to hear about over and over again. And this is where you design your data collection as part of the creation to make sure that you have those things that are in place. You're also considering ethics, and then you're also putting together your implementation plan. So your creation is a big step. And then what you're going to see is that learning engineering is not linear. You see all these arrows going back and forth because really what happens is once that you start this design, you want to pilot it and you want to test it and you want to see what's happening. So that's part of the implementation side of it. And you're seeing if the data that you're collecting is what you need and are your systems the way that you wanted to be designed. Then you use that data to investigate what's happening with the data. What did you learn? What changes and improvements that you can make. And so you're going to be continuously going back and forth. And then the Carnegie Learning case study is going to show you an excellent example of how this iteration takes place and how you can have nested learning engineering processes happening at the same time. Next slide, please. And so again, reiterating, learning engineering, it's contextualized, it's iterative, and it's data-driven. And this is where you can see what are some of those questions that you ask at each stage about the data. Looking at the challenge, what is the question that you want to know? The creation, what data do you need to collect? In implementation, are you getting that data? And then in the investigation, what did you learn from that data? And all driving toward outcomes-focused process. Next slide, please.
So as Jody mentioned, the learning engineering is a team effort, and the learning engineering uses the analogy of a flower where each petal represents a different area of expertise. It's important for designing educational applications. And the focus is, the most important part is the shared understanding. Each expert has a base set of common competencies and a shared understanding and shared vocabulary for the practice of learning engineering. And that's what we want when we have a team of learning engineers or other experts to work together to find and solve the central challenge. Next slide. So in this particular case, we are presenting the case study of pK-12 program, and it's a partnership between Carnegie Learning and CAST. CAST stands for Center for Applied Special Technology, and the project is to explore and support reading supports with a focus on how reading affects challenges for students who are using reading as a part of their math learning, and determine when to provide or recommend reading supports and scaffolds. So the project uses a lens, a universal design for learning lens, and specifically it's testing supports in math program, which is called Mathia, and it's funded by IES, National Center for Research, National Center for Special Education Research. The case study will be presented by Steve and Ray and Husni. Steve?
Thanks very much, Sarka. As Sarka mentioned, this work has been supported by the U.S. Department of Education. IES is their research division, and this is in partnership with CAST. And our challenge really is that in U.S. schools, there are many students who are English language learners who or otherwise have reading skills that are well below grade level reading skills. And we were concerned with providing supports for those students so that these students with reading difficulties can learn math as well as possible. And in mathematics, there's a number of cases with mathematics terminology as well as substantial language involved in word problems, which are a big focus of mathematics, particularly in middle school. And the next slide. So the work that we're doing was done within our intelligent tutoring system called Mathia. You can see a view of it here. In Mathia, students move through the curriculum, through topics in the curriculum that we call workspaces. Within a workspace, students will complete a number of problems until they demonstrate to the system that they have mastered all of the underlying skills or knowledge components that are associated with that workspace or that mathematics topic. So you can see here the scaleometer, these partially completed circles, is the representation that is available to the student about the system's judgment of their level of mastery on each of the underlying skills that they're going to do in this workspace. When they demonstrate mastery of each of those skills, they'll move on to the next workspace, the next topic, which will introduce new skills. Next slide. So you can see here, as I mentioned, the work we're going to be talking about is word problems. So you can see a word problem here. Students have a number of supports for solving these word problems. You can see there's a button there called Step by Step. That's a worked example that steps students through the problems. And there's a sample problem. Students can also ask for hints on each step. And one of the important factors in Mathia problems is they're not just provide the answer. We're providing the students with an interface that breaks the problem down into individual steps. And so we can understand the relationship between students' individual performance on smaller skills and then direct instruction to those smaller skills. It's also important we give immediate feedback and just-in-time feedback, meaning we not only provide feedback on whether an answer is right or wrong, but if it is a common answer that's recognized by the system, they'll get an additional message that explains why their answer was incorrect. Next. And so you can see the reading challenge here is in the word problems. There are a reasonably dense block of text expressing the background for the word problem. There is mathematical vocabulary. There is a glossary available for students. And when we talk about vocabulary, we'll talk about how that glossary played into some of our thoughts about improving this. And then also there are complex instructions for what students are doing. So when we think about these, you can see on the right the relationships between the kind of characteristics of the problems as students see it and the way we think about what kinds of improvements we can do to focus on those. So these dense blocks of text could be improved by having better tools for focus and attention. Vocabulary has to do with word reading and definitions, like with the glossary. And then these complex instructions can be a barrier to comprehension of the overall goals in the problem. Next slide. So I'm going to pass it to Husni to talk about some of the background research.
Thank you, Steve. So I'm going to start talking about some of the ways we developed some of the reading supports in Mathia, and we can go to the next slide. So we wanted to develop reading supports in Mathia, but first we needed to figure out which content would be most impactful if we built in reading supports into. And to do that, we had a data set of students' end of year exam scores on math as well as ELA, English Language Arts. And we were able to connect those scores with their performance within Mathia. So we were able to look at correlations between students' performance in Mathia and their ELA exam scores, as well as the correlations between students' performance in Mathia and their end of year math scores. And so we took the ratio of those two correlations as a way of figuring out how heavily does a lesson or a workspace, as we call it in Mathia, load on math versus reading. And that's how basically we identified some lessons where we would later on build in those reading supports. Next slide, please. So one particular lesson, or kind of a mini lesson that was very related to reading is this, what we call in Mathia, the pre-launch protocol. And this is really just an introductory activity in Mathia. It doesn't talk about math. It mostly just kind of teaches the student how to interact with Mathia, how to request a hint, how to use the glossary and use all of the features that Steve mentioned before. So it kind of makes sense that this would be related to reading because it's not really testing or helping students practice math in particular. This also has a nice feature that pretty much every student completes this. This is the first thing, pretty much every student completes in Mathia. So we have, performance data on this particular pre-launch protocol from the majority or the overwhelming majority of the students. So we were able to use performance on the pre-launch protocol as well as the ELA exam scores that I mentioned before to build a model using a neural network to predict students' reading ability in Mathia just from this introductory activity. So it took into account things like student correctness and number of hints they use, number of just-in-time feedback they receive, and the number of attempts they make to be able to make those predictions. And it worked surprisingly well. I sometimes say it works depressingly well because just from the first 15 minutes in Mathia, you can kind of tell with like 80% accuracy if a student is going to pass or fail their end of year exam scores in ELA, which is, even from a math platform like this. So this essentially allowed us to identify the target population of these supports, essentially, that we would later on be able to measure the effect of these supports on. And I will pass it on to Ray.
Cool. Thanks, Husni. So while Husni was conducting his brilliant work and figuring out how to target our population that we were interested in, we took the workspaces that were identified from his content analysis to kind of see, okay, so what content in Mathia really is related to reading. We came up with workspaces, and Steve had kind of given an overview that Mathia is organized into these workspaces. So our team conducted user experience research inside of those workspaces to help further identify what pain points are being experienced by learners. The high-level findings from this work are on the slide, but over the course of the project, we met with about 20 teachers and 30 students from 4 different districts, and we held surveys, one-to-one interviews, journey mapping sessions, focus groups, stimulated recall sessions, and additional design activities to specifically support some of the solutions we were thinking about and the discovery needs. So we continually involved our end users in the design process. Our project was also fortunate enough to support an educator advisory council. So this was a group of teachers who were selected for their experience and expertise. And we met with them over the course of the project to help in the generative and formative phases, in addition to those teachers and students who were using Mathia from our research partner schools. We can move to the next slide. And we took those findings, so seeing that students are really overwhelmed by large blocks of text, seeing that they are struggling with reading, that there's hint misuse, that they skip instructional directions, we took it back to our team to start to collaboratively generate ideas. And our team was truly interdisciplinary. We had experts from literacy and math content, instructional design, data science, developers, cognitive science, and we also had a technical advisory council, which consisted of highly respected educational researchers who we would bring our supports and ideas to for additional consultation. So really trying to pull together a collective knowledge and areas of expertise to find solutions that were respected and hopefully would work with our target population. Over the course of the project, again, we applied those co-design strategies and we used a universal designs for learning framework developed by CAST. It's really focused on removing barriers for learners. Barriers are in the environment, not in the learner. And we also applied principles from design-based research to refine and develop our ideas. So I want to show you a snapshot from our process. This actually, what you're seeing is a 30,000 foot view of Pittsburgh, which is where Carnegie Learning is actually located. And if you click one more time, this is our 30,000 foot view of one step in our process to arrive at solutions. So this is a Google Draw from a team exercise, one of many, where we collectively ranked our ideas. They're color-coded and represented on stickies. We brought in each team's perspective, so development perspective, content perspective, design perspective, to try to work out the feasibility and impact of each idea. And I really like showing this because the learning engineering cycle is a beautiful distillation of this process, and it looks very straightforward. But I think it's always important to point out that in practice, this type of work can get messy, and it truly is iterative. So through a lot of collaboration, creative thinking, and learning what strategies and channels of communication worked for our unique team, we were able to create solutions. And I'll hand it back to Steve to kind of share some of them.
Thanks, Ray. I do want to emphasize a big part of learning engineering to me is about understanding where to focus your efforts. And so, as Ray showed, like we had no shortage of ideas, some of which turn out to be good ideas, some not so good ideas. And so we're trying to focus our efforts, and part of what we're doing in that cycle is understanding, like, as quickly as and easily as possible, like which are the ideas that we really want to dig into and extend, and which are ideas that sounded really good in a meeting between these experts, but turns out empirically aren't really moving the needle. So we're going to talk about a couple of the ideas that made it through our first filter to get to be testing with students. The first one is a focus tool. So as we were talking about, students sometimes just feel overwhelmed by the text. And so screening out part of the screen we thought might be helpful to students. This is not an idea that we invented. A lot of tools do have these kinds of screening or focus tools. And so, but to our knowledge, nobody had ever actually tested the impact of these tools. And so you can see in the screen, the student would have a button to show or hide this focus tool. They can move the tool along the screen, so highlight line by line, close the tool again, and they can also resize both the kind of window within the screen and the size of the screen itself. So you could have it screen out, the whole screen versus part of the screen. So that's one tool we're testing. Next one. We talked about vocabulary supports, and there is, as we mentioned, a glossary. If you look on the top right, you'll see the word glossary, which is a clickable thing there, but it's a little bit out of the way for students. It's not so much in their face. You'll also see that there are hyperlinks in the text, within the text. Those, again, are a little bit subtle. And so what we did was increase the number of hyperlinks, and also there's a set of key terms, which are mathematical terms that are used within the lesson, that come up in an introduction to the lesson when the students go into Mathia, but many students ignore the introductory part. Students kind of click through because they want to sort of get to the work. And so the idea was to put the key terms sort of more in their face so that they see it right away. Next slide. And then the next one is simply focusing on the exact text that we use within the word problems. And this is the one that we're going to dive into most deeply. We worked with teachers and students, as well as reviewed the literature to understand what aspects of text might make it easier to read, particularly for students with reading difficulties. So a couple of things: reducing low frequency vocabulary, so less common words, simplifying the syntax, reducing the extraneous information, and improving signposting and organization. So just the ways that the wording cues students to what they need to do. And what we did was we worked with our English language team at Carnegie Learning to develop a style guide. And some of the things in the style guide have to do with using precise nouns and verbs, being very consistent in language, verb tense, removing passive language. And there were some things that were sort of math specific, in the sense of, like, one of the things that comes up is we would find the word amount used a lot in math problems. And often math problems are talking about amount of things, let's say, that you buy, and then also amount of money that you spend or earn. And it's really important to distinguish those different uses of amount. So we were very careful about always saying what we're referring to when we're using sort of quantity phrases like amount. And I want to say, like, whenever I present this research, my overall fear is that what you're going to see is our rewrites are very effective, and what you're going to think is, well, the problems were terribly written to begin with, and now they're well written. And that's actually not the case. So we have a little quiz for you now, and you can vote in the chat. One of this is the same word problem that was rewritten for the purposes of this study. And what I want you to do is read these two word problems and decide which one is the rewrite. So in the chat, post your opinion about which one is the rewrite, and also think about whether this decision is hard or easy. All right, coming in some mixed opinions. My high level judgment is that we have more votes for 2 as being the rewrite, but substantial numbers of votes for 1 as well. One of the things I'll say people often go by is they think that the rewrites will be shorter because we're removing extraneous text, but it turns out that that's not necessarily true. In some cases, the problems end up being shorter. In some cases, the problems end up being longer. One reason the problems might get longer is one of the things that we did in a lot of the problems was remove pronouns. So we would repeat a noun rather than referring to it with a pronoun, because pronoun references are things that introduce extraneous cognitive load and are also difficult linguistically for some students to understand. But I know you're dying to know the correct answer. And in this case, the rewrite is option 2. So one was the original problem. The other one is option 2, is the rewritten one is option 2. So next slide. So let's talk about how we implemented this study and the results. And Husni, take it away.
Great, thanks. Yeah, so we ran a few randomized controlled trials to implement this and test out the outcomes that I'm going to be talking about. We can go to the next slide. Yeah. So the Upgrade platform is our open source platform that was developed by Carnegie Learning to run randomized controlled trials in educational settings and be really scalable. So Upgrade is integrated with Mathia, but it is open source, so it can be integrated with a very large number of intelligent tutoring systems and other educational platforms. And on the right here is just a screenshot of the Upgrade platform. So we were able to run a few randomized controlled trials with Upgrade, and I'm going to be talking specifically about the word problem rewrites. So we ran two experiments, one targeting workspace in grade 7 and one targeting a workspace in grade 8. They were very similar workspaces, only really some minor math differences between them. So we had over 12,000 students completing at least one of those two workspaces. And they were randomly assigned either the original problems or the rewritten problems. And we looked at some metrics in Mathia to understand the impact of those rewrites. So we looked at one, the promotion rate. Promotion is really what we call when a student fails to master all of the knowledge components in a workspace. We move them on to the next workspace anyway, but we call that a promotion after they have worked through 25 or so problems. We just got to move them to the next one. So we want to reduce that promotion rate. We looked at the time spent, so how long did students take to complete these workspaces. We looked at the total errors that students made within those workspaces and the total problems they completed before they completed that workspace. Next slide, please. So here we're just showing a few results that we found, and just to explain what these figures are saying a little bit. So on the left figure is talking about the time students spent in those workspaces, and the one on the right is showing the errors per problem, the average errors per problem. The one on the left is actually the median time in minutes. So we had two workspaces. We're calling one of them integers and the other rationals. That's really the only difference between them, is that the 7th grade workspace uses integer numbers and the 8th grade one uses rational numbers. And then in blue and orange are the control invariant groups. So what we really find here is that students were able to master more content. They were making less errors, but they were also doing so in significantly less time. And that's particularly true for the 7th grade workspace. Which was a pretty nice result for us to see that we were improving the error rates, as well as allowing students to have now some extra time that they can spend on other content. Next slide, please. Yeah, and that's pretty much it. We're just now kind of restarting this cycle and doing more experiments, some of which involve the use of AI, for example, some of which are digging down deeper into smaller changes to understand exactly what worked in those rewrites. Yeah, we're going to be running, or we are continuing to run more experiments along those additional follow-up studies. And I think we can take questions now. Thank you.
Yeah, can I ask one? This is Ian Gibson from Republic. Um, is everybody hearing me?
Yes.
Yes, we hear you.
Oh,
Yep.
great,
Sarka, were
thank
you
you.
going to manage this?
Okay, so can I go ahead and ask a question?
Please go ahead, Ian.
Yeah,
Yes,
so
yes.
with regard to the creation and iteration phase, I wanted to just get a bit more clarity on how you have this big team of experts of all different disciplines suggesting improvements and doing rewrites and changes. How much of the Mathia or the Mathia combined with Upgrade platform user interface is instrumented for analytics? Can you actually tell all the different user interactions that occur when people are clicking or not clicking on things? And if it is instrumented enough, can you then do just sort of pure data mining, to check for uh, omissions, errors, roadblocks, performance issues, rather than just doing A/B testing when you make a change?
Yeah, I could talk about that. One of our advantages with Mathia is we have instrumented it, so we know and collect data on each kind of entry that a student makes. So if you want to go back to one of the screenshots of Mathia, we can sort of look at it. But some of the problems there, like filling out a table or doing a graph, each of those entries, like each cell in the table, when the student submits an entry and gets immediate feedback, we will know exactly what the student entered, whether that entry was considered correct or incorrect, whether they received feedback on that entry, and then also hint events. So when they asked for a hint or got feedback on an error like that.
Okay.
And so we do have that data. An example of a data mining study was, as Husni described, so that pre-launch protocol, which is the non-math kind of introduction to how to use Mathia, is actually built just like Mathia, so it's instrumented in the same way. So the data mining that Husni described about using performance on that element of the program to infer students' reading abilities is exactly an example of sort of using data mining to understand student performance.
Great, thank you. On a very quick last note there, right at the end, there's a very interesting finding there. I thought that it takes longer to make mistakes; it's quicker to do things right. That's a
So
beautiful sort of
almost always
finding.
true. Yeah.
Well, you want to think that's true, but the kind of curmudgeon view would say, well, the students are being slapdash and trying to go too fast. That's why they make so many mistakes. But those data prove that's wrong, right?
Yeah. In this case, there's always more to learn. Yeah. There may be instances where it's not like that, but yeah.
Thank you.
I'll go ahead and chime in here. We have a question that Anna's already addressed, but I thought maybe we should do this out loud. And that was this was from Anil, and says, "Great case studies. What do you suggest for someone who wants to implement learning engineering in their instructional design? Where should they start? What small step can we start with?" Anne has recommended to start at the toolkit. And Steve and others, any other thoughts?
I think at a high level, one of the things that the process that Ray showed was to help refine questions. So you often start with a big high level question like, how can we improve student learning? Right? But what you want to do is break that down into like components of, well, what are the barriers to student learning? Like, do they understand the instructions? Do they understand the user interface? Or, like in this case, you can sort of think about language as being a barrier to students getting at the mathematics content. And so then we talked about, well, what aspects of the language might compose that barrier? So breaking it down into like a practical, smaller question about improvements that you can make, and then you follow that up with the instrumentation if you don't already have things instrumented. I should say, like, one of the reasons, so we were able to, as Husi said, like collect data from 12,000 students. That's partially because, and pretty quickly, that was in, I believe, like 6 weeks. That's partially because Matthew is being used and all that, but also like a big part of this is we had already instrumented Mathia to collect that data. And because Mathia is this mastery-based system, we have outcome measures that are sort of integrated into the system. So we didn't have to insert an additional test, either an ELA, an English reading test, or a math test in order to do the study. That's a great situation to be in. It just makes things a lot cleaner. There are always concerned sometimes about doing intrinsic measures versus sort of more extrinsic and valid measures, but that's a great way to start.
I'm going to provide a quick answer to this as well, and that is that with my development team, one of the things that we've done, this is a little cheat, which is um, even if you were not using learning engineering processes as part of your development process, I find going back and reviewing the work that you did previously and fitting it into that process gives you a new sense of how it adds value to the process that you're doing. So sometimes going back to an existing bit of work that you're doing and understanding how that might be affected by the learning engineering process and documenting that really makes it easier as you're moving ahead to then do it with your next project or next iteration is another way to make use of this.
I had a question, and this is more, I think, about transfer. Stevie had indicated that, like, really trying to discern what the issues are, like in the very beginning, when you're just creating the platform, coming up with what are the difficulties that students might be having when they engage in the platform itself, which is great because I think, like, you can do that in the beginning rather than try to retrofit things at the end. But my question was more about like the long range outcomes that you might be interested in. So, for instance, like, I, I've studied many tools that like the kids get really good at the doing the thing in the tool, but then it doesn't transfer to something like a teacher made test, doesn't transfer to like a standardized test or something like that. So I was wondering about like what the longer term outcomes of this project were, if any.
Yeah, that's a great question. And it's probably one of the most difficult things in education is how you trade off short term to long term. There's all sorts of cases where you can improve performance in the short term and not in the long term, or you can improve performance on sort of a narrow thing, but doesn't transfer to what you really care about. So that's kind of the counter to the intrinsic measures, which are almost always sort of closer to the manipulation that you do. So we do, as part of this project, also collect, not for all these 12,000 students, but for there was a subgroup of schools who we had research agreements with, who agreed to give us outcome measures from the state exams that students take at the end of the year. And so we're looking at impact on those exams in addition to the kind of proximal measures that we're talking about here. Right. And it's it's harder to show impact on those measures because there's a lots of things other than, this, like Husi talked about, we changed, typically there were two workspaces, but an individual student would probably only see one of those workspaces out of sort of 60 to 100 workspaces that they would go through in the school year. So showing an impact on that final exam based on what's ultimately a small manipulation is much harder. And
Yeah.
part of what we did was bundle together. We didn't talk about the focus tool and the vocabulary improvements and the idea, but the idea was to bundle together a bunch of improvements so that as a whole we might move the needle on those end of year tests.
Yeah, that makes sense, especially when if if you have to go back to like to iterate afterwards. If you don't get the results that you want on these measures of transfer, you have to iterate, afterwards. It can, take a long time. I guess my only other question, is kind of related to that would be, what is the timeline like from the beginning of when you started and to kind of where you're at right now?
Gee, so this grant started 4 years ago. Is that true? So yeah, uh, my experience in grad school was always like, you start reading papers and you're like, oh, this research probably took, a month or two, right? And then you get into it and you realize everything it does take a while to iterate through these cycles. So from beginning to where we're at now, it's about 4 years. Now that's more work than we've talked about here, but it certainly takes a substantial amount of time and iterations.
Yep, that tracks. That's what I would have expected for sure. Thank you.
Yeah.
Appreciate it.
Other questions? There's one from Liza Loop in the chat. Since you also have data on background barriers, maybe there's an opportunity to look for correlations among that and the Mathia data. Have you done any of that?
Liza, can you talk a little bit about what you're thinking about in terms of background barriers?
Well, at the very beginning of the session, and I'm not familiar enough to name who was talking about it. Maybe it was Ray. That there was some work on the environmental barriers for learning, and often we do research where we create a laboratory or an online or a carefully curated study, and we ignore some of the other information that we have, like the ACE background, the adverse experience background that those 12,000 students have, or very current information that may be going on, for example, home stresses that can seriously impact, or we just had a recent earthquake here in Northern California. So events that we wouldn't anticipate in doing the study design 2 or 3 years ago would have an impact on the performance of students on the day that the data was collected. So that can really skew our data. And unless we're looking, the old-fashioned way of saying this is notice whether the laboratory door was open or closed when you did the physics experiment. So
Right.
I'm always looking for the things that people haven't done, and I don't mean that as a criticism of what they have done. It's just let's always look at the boundaries of the system. Did that answer your question?
Yeah, it's definitely a concern, right? So part of the logic behind random assignment is to kind of even out those things. So on the day or days that the experiment takes place, students who may be experiencing, some particular issue would be sort of evenly spread out among the conditions. That's the hope with randomization. There's always a concern that there could be some interaction, though, right? And which can affect your results, definitely. And yeah, and
collection of data might help us with that particular problem. That's all I'm pointing at.
yeah, there were a number of questions in the chat about ethical issues as well. And I'll just say, like, so first of all, we didn't describe, like, Mathia is used as a kind of regular component of mathematics within our core math curriculum. And so the usage is kind of like within public schools, typically, on typical public school days. It's not a special day where they're doing this experiment. And so that's our population. But also, we don't collect more data than we need from the students who are using our application, which means we know actually very little about them, right? They log on, they're in a math, we know they're in a particular math class in a particular school, but we don't normally collect demographic data or attitude data or, any sort of information about them other than their membership within that classroom. Now, for the purposes of a research study, so we have these 12,000 students who we know relatively little about, and then we have a smaller group of students where we're working directly with those school districts. So like I said, we can get their test score outcomes and demographic information as well to check that. But that's just part of our stance, the kind of protecting student privacy, and is to know as little as possible. And that's a barrier to doing some kinds of research.
Steve and Husni and Ray, are you able to stick around after we officially close the session to answer any questions? If you can, we're going to keep it open a little bit later, but I need to go through the last bit of slides we have here.
I can say a few minutes, yeah.
Okay, thank you, Steve, so much, and to your team, Husni and Ray as well. Thank you so much. John, let's go to you.
Hey, everyone. Hi. I would like to introduce you to a very important structure within the IEEE Standard Association, the ISICLE group. We have a structure we call special interest groups, or SIGs. You'll see them on the diagram here, and market interest groups, or what these are called is MIGs. And they're designed to kind of foster collaboration between various professions and aspects of the learning engineering environment. So the MIGs focus on specific market segments. We've got a pre-K-12 education one, a higher education, a workforce, and a government and military MIG. And each of these MIGs is dedicated to understanding unique challenges of that domain. The SIGs, on the other hand, these are cross-cutting and they apply in all of the MIGs. So the Design for Learning explores how to optimize educational experiences, tools and instrumentation. They focus on technology that powers these learning solutions, companies, credentials, curriculum. They're examining how to define and measure success. The student graduate one is centered on the learner's journey and career development in learning engineering itself. And then translation, localization, self-explanatory. This is part of the learning experience. So think of these MIGs as the what and the where for specific market needs, and the SIGs are the how. How do we get this done efficiently? As part of your journey through developing yourselves as learning engineers, we kind of urge you to reach out. This next slide here has all of the contact information for each of these. Feel free to reach out if you use that QR code. That will get you to the IEEE ISICLE site, listing all the MIGs and giving you even more detail on each one of them. But please reach out. You don't have to be a member of IEEE in order to participate, and we welcome everybody's experience and interest. So,
great.
Back
Thank
to you
you
guys.
so much, John. Yeah, really appreciate that. So next slide. Just lastly, there are a whole lot of resources that are available. Actually, we just put up a poll. If you indicate which of those SIGs and MIGs, you can select any or all, any combination thereof, just so that we know where interests lie. And I like to say this is where the real work of ISICLE gets done. So I urge you to get involved in SIGs or MIGs that address your interests. There are a lot of really rich resources available in both the ISICLE community as well as at the Learning Engineering Hub put together by the Learning Agency. And you can see the QR code here to get to those resources. There are a number of books, posters, and some really nice tools that have been developed as part of the ISICLE work. So evidence and decision tracker, case study guide, maturity model, and other things that are coming out of many of the people who are participating in ISICLE. Last slide, please. So, as I say, now's the time to get engaged. If you are waiting for an invitation, this is it. So get involved with IEEE Icicle. You can send me an email. You can send any of us. There's emails for the people who presented on this, although not the Carnegie Learning team, and urge you to get in touch. And I look forward to you being involved. We'll send an email out to you with some of this information as well. So thank you so much. And thank you to our Carnegie Learning colleagues for presenting your case study. We'll be doing this again, and we'll be reaching out in terms of other market segments. So look forward to having your participation. Thank you, everybody.